So the next speaker is Lilith Hafner, talking about sorting. So Lilith is a prolific Julia contributor, to say the least. Lilith is a very frequent contributor to the bi-weekly triage calls that we hold, and has done a huge amount of work on sorting. And I'm really looking forward to this. This should be very interesting. I believe we have some of the coolest sorting libraries out there right now in our standard library, thanks to this next speaker. So please take it away.
About sorting. That's base.sort.sort. Okay, so what are we going for with sorting? This is like if you're sorting a vector. If you've got like 732 and you want 237, you call sort on it. The main goal here is for it to be easy to use. You just, like, most of the time you want to sort something, you just want it in order, and it's not performance critical, and you just want it to work. And that is like priority number one. Priority number two is high performance. Let's make it fast whenever possible. And in many cases, we can get it really fast. Although, just a note, if sorting is your bottleneck, you're probably doing something very wrong. But if that's the case, then Julia is a good language for that. Anyway, some other things we want for sorting is for it to be extensible and customizable. So you should be able to sort any sort of element if you provide a way of comparing them. And even more optimizations for elements. If you have a package that defines certain structures or data types, whether it's a collection or an element type, then you want it to be able to be more efficient. It should be extensible. So there's actually a lot of things that we can do with sorting. The domain space for this design is pretty broad. We want to support custom container types. We want to support higher dimensional containers. That's like a matrix or just like an n-dimensional array, which will sort each slice as opposed to sorting the slices. Anyway, we want to get sort perm as well, which is getting a permutation that will put your data in order. So if you have a data frame and you want to sort it according to the first column, you might want to get the permutation that would put the first column in order and then apply that permutation to all the columns of your data frame. So in general, sort perm is something that we provide, as well as partial sort. You can sort a vector, and you can sort a view of a vector, which will just take a little section and put that section in the correct order. A partial sort is slightly different. If you, say, have a vector and you want the top 10%, you want to find them and sort them and put them in the right place, that's what partial sort does. So it sources data from the whole vector and just places them correctly for part of it. We also want to support custom ordering. So you can put things in reverse order. You can sort it by a certain function that's applied to the elements before comparing. So if you have a bunch of people and you have a field height, you can sort by height, and that will give you arrange people by whatever the function provides. Sometimes that's not possible, and you want to provide an arbitrary comparison function, and that's also supported. But there's some considerations for performance. This isn't a but. And there are some considerations for performance and for some other factors that we need to think about when making these systems. Oh, this is starting to give a little bit of feedback. So known types and orders. If we have some common case that's well known, we should be able to have really good optimizations. So if we're sorting IEEE floating point values into ascending order, that's something that's well known and we should have a good, efficient algorithm for, and we do. Patterned input order is another thing we want to take into account if it's partially sorted already. We don't do a great job of taking that into account. If it's fully sorted, we do, or if it's reverse sorted, or several other special cases. But in general, patterns can be taken advantage of, and that's a weakness of the current system. Input size, we want to be able to support different input sizes A small input should have a simpler algorithm, whereas a large input might warrant a more complex algorithm. It varies based on the machine specs, and those are all for performance. And then stability is another consideration we want to think about. And this is, I mean, I'm listing all these things to kind of justify why sorting could be complicated, because there's like more to it than originally it seems like. So stability is if two elements compare equivalently, that is, one is not less than the other, and the other is not less than the one, you don't rearrange them. And so if we are comparing people by age, and two people are the same age, we don't want to swap them if it's stable. If it's an unstable algorithm, we're allowed to swap them. And so some domains require stable algorithms, and some do not. And then, of course, there's extensibility and backwards compatibility. If someone's done something before, we want to keep allowing it in the future. So there's a lot of optimizations we use. I'll get into these later. But first, just want to give like a higher level picture of what this call stack looks like. When you call a sorting function, whether that's partial sort, whether that's sort, whether it's sort bang, whether it's partial sort perm bang, whatever it is, and whatever input types, it gets reduced to sort bang and sorting an abstract vector. So if you want to sort an array that's multidimensional, we sort a bunch of vectors. It gets reduced to that. If you want the sorting permutation, the permutation that will put something in order, then we sort an array of indices, and we give a custom ordering, where we say an index is less than another index if the values, when you look it up in the data, are less. And for like an iterator, we'll collect the iterator and then sort the collected result. And all of this then gets passed to this underscore sort bang function, which is new in Julia 1.9, I think. And that is an internal function so that we can be very clear that it's subject to change, and it does all the magic, and it has all the optimizations, and it's internal because we want to be able to change those optimizations, and even the design of underscore sort bang. So how does underscore sort bang work? That's like how this becomes fast, how we have a system where we can fit in more optimizations after the fact, how packages, if they're willing to muck with internals, can fit in optimizations. It looks kind of like this. There's a bunch of methods for underscore sort bang, and they're dispatched based on the algorithm. So the algorithms are nested, like this would be how you would call it. So check pre-sorted is an algorithm, and when you call sort bang with that algorithm, it will dispatch to that first method that's listed, because the algorithm is a check pre-sorted algorithm. And then what that method does is it checks if the input is pre-sorted. If it does, then we're good. And if it's not pre-sorted, then it moves on to the next algorithm. And this lets us come up with a bunch of independent and rearrangeable methods, and then put them together with nested algorithms. And it lets people modify those algorithm lists if they'd like. And it creates a way to reuse these optimizations in different places. So we might want to use insertion sort in more than one place, and we can describe that using this algorithm type. It becomes almost a domain-specific language, the algorithm type. If we wanted to not check if something was pre-sorted, we could call it like this, without the check pre-sorted type, and then it'd dispatch straight to insertion sort. This is not an excerpt from Julia source code, from base implementation, because why would you check pre-sorted before insertion sort? Because insertion sort's really fast on sorted data. It's just an example. I should have said that at the beginning. Anyway, what else is going on here? There's this keywords function. This KW stands for keyword. Those are kind of weird. Why that's there is to pass around dynamically scoped variables. There's a lot of things you might want to keep track of in sorting. You might want to pass things from one method to another, from one optimization to another. Like low and high are the first and last index that are going to be sorted. If you're working with partial sorts, those can contract as you realize that only a sub-region is of relevant interest. Or you have an optimization that, or just an algorithm that breaks up the input into two parts, and then you want to sort them recursively. You should set low and high, and those should be passed through all the methods. And some other ones you might want to keep track of are minimum and maximum, which is the extrema of the input. And that's useful for optimizations of all, whether you can do counting sort reasonably. Counting sort relies on a very tight range between minimum and maximum. And once you've computed it once, you don't want to recompute it. And I also don't want to pass that through each method explicitly. And so that this keyword mechanism provides that. And I use it instead of, I use a named tuple in the argument position instead of keyword args, because it allows dispatch, and there's zero overhead. It's kind of like globals and kind of like keywords, but it allows dispatch and there's no overhead, no recomputation. And so it's as if I was passing them all through explicitly in positional arguments, which, I mean, that is what's happening. It's just, you can't really see it because it's hidden away. And there's this scratch space thing. Some algorithms want scratch space, like scratch quicksort, like radix sort, like merge sort. And we only want to allocate it once. There should not be, when working with scratch space, you don't want to like make a scratch space, let it be garbage collected, and make a new one. If we had great escape analysis, that might be fine. But without that, we need to allocate it once and then pass it around. And the tricky thing in here is we can't allocate scratch space at the top level and pass it down the call chain, because at the top level, we don't know if we're going to need it. We don't know what algorithm we're going to dispatch to until we've done some analysis. We don't know if we're going to need the scratch space, and we really don't want to allocate if we don't need it. So for that, we need to pass it up the call chain, because we might go down one branch, realize we need scratch space, and then finish up, come back up, go down another branch, realize we need scratch space, and we want to share that. So this is even closer to a global variable than what we were working with before, but it's still implemented with zero overhead. We're not actually using global variables. It's just similar to that behavior. And the way we implement this is by returning scratch space. How do you get something up the call chain? You return it. So this underscore sort bang returns scratch space, not the sorted vector.
Does it always return scratch space or keyword?
It only returns scratch space. Maybe it should also return keyword. Yeah, so for the other keywords are low, high, min, and max. Low and high, it makes more sense to do like a recursive paradigm, because when you set low and high for a sub-algorithm, you don't want your parent to have that restricted low and high as well. Whereas scratch space is kind of different in that way, that it's just passing it around. It doesn't matter what happens to it. There's very little semantic in the scratch space. In retrospect, this keyword design was made before I knew what a dynamically scoped variable was. Maybe this should be changed. This is letting folks, this talk is giving you a view of what's going on right now. It's still internals, it's still subject to change. I appreciate where it should go. Yeah. Anyway, this is a screenshot from a REPL. This is the default stable sorting algorithm. Fun fact, this looked so bad. This is custom printing for the algorithm type. It was a lot worse without that custom printing, because this predated abbreviated type signatures. So it was I mean, this is O of n. It was O of n squared length. Yeah, anyway.
What's n?
N is the number of nests. So if you have something of a type, nested types like check pre-sorted, if you nest that n deep, then the length of that without abbreviated type signatures is O of n squared.
Every other type contains references to line number types.
Yeah, really bad for SciML. Anyway, if you have nested types, the default printing from like Julia 1.9, maybe 1.8, definitely in 1.8, very poorly displays, very large. Anyway, we've fixed that. But this is
what we're using now.
yes. This is the default algorithm. And let's walk through, I mean, one caveat, like maybe this is bad. Like, does anyone really care about sorting performance? Unclear. If the answer is no, maybe we should just revert all this. Like, this might have been a mistake, but this is currently the case. So the first thing we do is a missing optimization. So if the element type is a union of, say, float 64 and missing, then we'll be like, wait, hold on, okay, 15 minutes, this is great, there's plenty of time. We filter the missings to the end. Like sorting filters missings to the end. That's just in the doc string. Missings go at the end. Some people want to be able to put missings elsewhere, but not enough people have asked for it to put it in base. We'll see where that's going. Anyway, this optimization does that at the beginning. By default, what we would be doing is using the comparison function and see like, is 4 less than missing? The answer to that is no. Missing is greater than 4. And that comparison.
So everything just blows up.
Well.
Oh, it's the is less function here.
Font size.
Thank you for the font size. Anyway, this is slow because there's like dynamic dispatch almost. I mean, probably not dynamic dispatch because unions with missing are efficient, but we don't want to be doing that. We'd rather first filter all the missings to the end and then work with non-missings. So, what the? Okay. Why is my camera on? That's creepy. Anyway, Microsoft PowerPoint. So missing optimization filters all the missings to the end and then wraps the remaining vector with non-missing vector, which is an internal type that has an L type that is not missing and just asserts that it's not missing. So then you've got a not missing vector wrapping a vector with L type that's a union with missing. And we just assert that all the missings are at the end. And we enforce that by when we construct the thing, we put all the missings at the end. And then we proceed with whatever's next. Or if that optimization wasn't applied, we just proceed with whatever's next right away. Yeah?
When you do the missing check, you have to scan for the missings and then you do the is sorted check. Is that fused somehow as an optimization? Because you can do the both checks at the same time.
Yeah, that is not fused. And have I actually benchmarked fusing those? No, I haven't. Maybe it is faster. I think that it probably won't be much faster, but
It's reading the memory, I guess.
yeah, it could be.
Since you have that beautiful slide up there, a question, how do you come up with such new listings? In particular, given similar to the previous question, that some of these checks for making decisions also have the runtime cost.
Yeah.
So how do you come up with this? I mean, like, is it a lot of trial and error? Like, you know nothing about sorting. So
Yeah.
how much is trial and error? How much is known in the discipline?
A lot of trial and error, a lot of benchmarks, and a lot of these are free. The missing optimization is free if the L type doesn't have missing. The bool optimization is free if the L type is not bool. Most of these are free or very cheap, except later down the chain there get to be some expensive ones, but they're warranted because they allow for much faster algorithms. And it's in trial and error. As for fusing missing and is sorted, most inputs aren't sorted. If your bottleneck is sorting and your inputs are typically sorted, what am I here for? So.
Usually do B time on the sort, and then after the first iteration, it's always sorted.
Yes, that's something to be aware of when benchmarking sorting. If you're benchmarking an in-place sorting operation, you need to set evals to 1, or you need to copy in the data. Because otherwise, very easy to be like, wow, this sorting algorithm's really fast. When you do at B time sort of X, no, that's bad. Anyway, okay, so bool optimization is next. This one was to prevent a regression. I did some stuff and I had a regression for sorting Booleans. Sorting Booleans? What? Why would you do that? I don't know, but I didn't want a regression. So sorting Booleans, you just put the falses at the beginning and the trues at the end. There's a special case algorithm for that. There's some compile time cost, but who cares about time to first X? This is Julia, right? Anyway, it's also in the sysimage, so it's probably fine. I don't know. Yes. Yes. Counting sort, though, allocates a vector. And yes. So anyway, once you've done those, if you've got fewer than 10 elements, you should just use insertion sort. And that's the next step. That's small. Base.sort that's small is an algorithm that has a parametric type. So that 10 is actually a compile time known constant. Then 10, we use insertion sort, which is that next one on the list. And if it's more than 10, then we use the IEEE floating point optimization. This one's actually a pretty old optimization. What it does is if the input is a vector of IEEE floating point numbers, all of the same size, and we're sorting it in ascending or descending order, then we can use a cool property similar to missings, how we didn't want to compare and check if something's missing. Floating point comparisons are a little slow, nanoseconds slow, but still could be faster. It's faster to compare integers. So what we do, and the reason floating point comparison is slow is because nans. Nans. So we want to swipe the nans to the end, and then also partition based on if it's greater than or less than 0. Because the bit pattern of floating point numbers is not quite the same as the bit pattern for integers with respect to comparison. You cannot reinterpret a floating point number as an integer and get the same order of comparison, even without nans.
It's just the sign, the negatives are in the wrong order.
Yeah, the negatives are in the wrong order. Bummer. So we split them based on positive and negative, and then reinterpret as integers, both halves, and swipe the nans to the end. And I think all that's in one pass. Yeah?
So going back to the bool optimization, what's the reason, is there a reason we do this instead of just doing a kind of an explicit shorter dispatch for Booleans, with a different method?
Yes, there is. If we, what? Oh yeah. Is there a reason we use this giant nasty system instead of just normal dispatch for bools? And the answer is yes, there is a reason. Also, the question was not that meanly phrased. It was a very kindly phrased question. Anyway, so one reason is if you have a union between missing and bool, what this optimization does was first do the missing optimization and swipe out the missings, and then can still do the bool optimization. So rather than method ambiguity of is it a union with missing? Yes. Is it a bool? Yes. I guess it wouldn't be a bool at that point. what we have is like an order. And another reason is because this lets you, I don't know. Yeah, that's the main reason. And because this is like a homogeneous system, to avoid ambiguity for dispatch, all dispatch for underscore sort bang is determined based on the algorithm. And so that means there's going to be no ambiguity. It would be possible to do it a different way, but this works and has zero overhead, so that's why we do it that way. So after IEEE floating point sorting is checking if it can be mapped to unsigned integers. And that's what I was talking about with these IEEE floats, how you can once you have them all the same sign, then you just reinterpret them as an unsigned integer. Or a signed integer, I don't remember. Either, great. We do one of them, I don't know which. It was a while ago. And there are you can reinterpret chars as unsigned integers. You can reinterpret signed integers as unsigned integers. You need to do a little bit of bit twiddling to get signed integers to be reinterpreted as unsigned integers. But it's worth it because then you only have to support, for these checks, for these counting sort and radix sort algorithms, we only support sorting unsigned integers in forward order. So we do a little bit of bit twiddling and then sort using really, really efficient O of n algorithms whenever possible. And there are some cases where we could extend this. It's possible to reinterpret tuples as unsigned integers and sort accordingly. We don't do that, but it's possible in some cases. So then if it isn't reinterpretable as an unsigned integer, we check if it's sorted, and then we perform scratch quick sort if it's not sorted, with insertion sort as a base case. Stick around for later for what scratch quick sort is. Anyway, if it is reinterpretable as an unsigned integer, then we try counting sort if appropriate, and we try radix sort if appropriate. And to do those, we need to compute the extrema. That's the minimum and maximum value, so that we only have to radix over the necessary bits, and we only allocate what's necessary for counting sort. And then we also consider insertion sort or maybe scratch quick sort, all based on the size of the input and the range of inputs. So that's all. That's the current system. Limitations: the internals are complicated and hard to work with because they're complicated. And when folks start depending on the internals, this is going to be such a mess to maintain. Don't depend on the internals, folks.
Who needs to depend on the internals?
I guess sorting algorithm wants to hook into them to add new sorting algorithms.
Yeah, and that's why sorting algorithms, old versions of sorting algorithms are broken on new versions of Julia, because they depend on the internals.
Is there anything else that cares about this?
I don't think so. Yeah. Don't do it. I'd like to thank Nicole Eichmeyer and Peter Michael Osera for funding this presentation happening. A lot of people helped review and contribute to discussions and such. Special shout out to Lucas Schwart and Jeremy Knussel. I've never met them in person. I don't know. They're just like random people who helped with documentation. Thank you so much. Anyway, that's all. Do we have time for questions after? Or was that countdown to end to end?
Yeah, sadly, we do not have time.
Okay.
We had some questions throughout first,
Yes.
fortunately. So yeah, we do not have time now. We've got to move on with Mosé. But thank you very much.